Hey guys, today we're going to be talking about the scale that we use to put a better number on the hydrogen ion concentration and the hydroxide ion concentration that we have in our solutions. Okay? Let's get started. We said previously that water will self-ionize, producing equal amounts of hydrogen ion and hydroxide ion. So if we're writing a K expression, an equilibrium expression for this, we would say the KEQ is equal to the hydrogen ion concentration and the hydroxide ion concentration, our two products divided by our reactant. But again, since water is a pure substance, we don't include it in our expression. So therefore, our KEQ is equal to this. Because it's water, we have a special way that we describe this particular equilibrium constant. We call it the KW. Makes sense, doesn't it? Experimentally, we can find the concentrations of the hydrogen ions and the hydroxide ions in pure water at 25 degrees Celsius. It turns out that both of them have the same concentration. 1.0 times 10 to the negative 7th. So, the value for the K of water, the KW of water, is 1.0 times 10 to the negative 14th. Hydrogen ion concentration and hydroxide ion concentration in a solution always comes out to be 1.0 times 10 to the negative 14th at 25 degrees Celsius. Here's why. Let's say we have our solution of pure water. And then we add in some hydrogen ions. What's going to happen? Those hydrogen ions are going to react with the OH ions, creating more water molecules, and in the process, it's going to decrease the amount of hydroxide ions while increasing the amount of hydrogen ions. Get it? The other way is true with OH. If hydroxide ions are put in that solution, well, in that case, they're reacting with the hydrogen ions, producing more water molecules, but decreasing the hydrogen ion concentration in the process. So we get more hydroxide ions and less hydrogen ions. So you get the picture? It means that when we multiply the hydrogen ion concentration against the hydroxide ion concentration of a solution, it will always come to 1.0 times 10 to the negative 14th at 25 degrees Celsius. Now you're at the pool, right? And you see the lifeguard at some point, and that lifeguard will say, "Everyone out of the pool!" And the lifeguard pulls out this case with some tubes and with some dropper bottles in it. And he or she will walk up to the pool and pull some water out of the pool in a tube and then put some drops of something in there and shake it around. And then they'll gaze up at it like they're the only one that knows how to do this. You need to back off. This is professional at work. Yeah. What they're doing is they're testing the pH of the water. pH is a scale that we use to determine the hydrogen ion concentration of that solution. And the pH scale goes from 0 all the way to 14. The way we figure out pH is really simple. You take the negative log, so you have to use the log button on your calculator, the negative log of the hydrogen ion concentration. For instance, if we took the hydrogen ion concentration of pure water, that would be 1 times 10 to the negative 7th. And if you plug that into your calculator and hit negative log of 1 times 10 to the negative 7th, you'd get 7 as your answer. That's our point of neutrality. That is neither acidic, which is from 0 to 7, and it's not basic, which is from 7 to 14. But right there in the middle is where pure water is. That's what we call neutral. But again, anywhere from 0 to 7 is considered to be the acidic range. And anywhere from 7 to 14 is considered the basic range. A few things of note. Battery acid, that's a 0. It's extremely acidic. Your stomach acid is about a 2, roughly. Soft drinks are about a 3. Vinegar is about a 3.5 or so. Tomatoes usually about 4.5. Coffee is about a 5. Milk is just under neutral. It's about a 6.5. Your blood is about 7.35 to 7.45, somewhere in there. Seawater is about an 8, antacids are about a 9.5, detergent about a 10, milk of magnesia is about a 10 2/3, household ammonia is almost to a 12, and then oven cleaner, very, very corrosive, is at a 14. So it gives you some idea of the different pHs along the way. Something important to note, since it's a logarithmic scale, that means that for every number, going from 4 to 5 for instance, we are going up by a 10-fold increase in hydrogen ion concentration. So going from 4 to 2 would mean we were increasing by 100 times our hydrogen ion concentration. Now, sometimes it's easier for us to talk about things in terms of OH concentration, hydroxide ion concentration. Well, guess what? We can figure out pOH in the same way we find pH. We take the negative log of the OH concentration. Remember how I said that hydrogen ion concentration and hydroxide ion concentration were inversely related. When one goes up, the other goes down, and so forth. Because of that, we know that when you multiply these two together, you always get 1 times 10 to the negative 14th. So the relationship, as it happens, between pH and pOH is this, that pH plus pOH always equals 14. So if you have the pH, you can always find the pOH. If you have the pOH, you can always find the pH. Now what if you're figuring in the opposite direction? Let's say you have the pH or pOH, but want to find the hydrogen ion concentration or the OH concentration. Since log is base 10, it's really simple. For hydrogen ion concentration, you calculate 10 to the negative pH power. Or for OH concentration, you calculate 10 to the negative pOH power. Something else to consider. Let's say you have a strong monoprotic acid. It only has one hydrogen to give, like HCl or HBr. Well, it's really easy to find out the hydrogen ion concentration in that case because the hydrogen ion concentration is equal to the molarity of that solution. So for 0.5 molar HCl, your hydrogen ion concentration would be 0.5 molar. The reason why is, recall that for strong acids and strong bases, they dissociate completely. There's not anything left over, and so what you see is what you get. So the same thing can be said for strong monoacidic bases. In other words, bases that have one OH group to offer. The same way, the OH concentration is equal to the molarity of the solution. So 0.5 molar NaOH means you have 0.5 molar OH concentration. But that process doesn't work for a weak acid or a weak base. Let's say that we have a 0.5 molar solution of acetic acid. The Ka of acetic acid is 1.8 times 10 to the negative fifth. Since acetic acid doesn't completely dissociate, we can't make that same assumption that 0.5 molar acetic acid means we have 0.5 molar hydrogen ion concentration. So how do we figure out the hydrogen ion concentration with this in mind? Here's how. We put together something called an ICE table. ICE refers to initial concentration, change in concentration, equilibrium concentration. So what I do is I put my reaction on the board. And to simplify things a bit, I've left water out. We understand that water's there. We know that some of the acetic acid is going to dissociate, forming the acetate ion and the hydrogen ion. Now we're starting with 5 molar acetic acid. Let's think in terms of that acetic acid going into the water. Now immediately after it goes into the water, at the immediate start point, there are no ions. So we would say that the initial concentration of our ions would be 0. You get it? All right. So initial concentration for acetic acid is 0.5. The initial concentration of acetate ion is 0, and the hydrogen ion is 0. Remember the marker, right? 1 and 1. These are both the same concentration. So one of these gives me one of each of these. Both are the same concentration. All right? The change that happens, we'll say, is X amount. So I'm going to lose X amount here, and I'm going to gain X amount here and here. Remember, it's all 1 to 1, isn't it? So I lose X amount here, but I gain X amount here and here. Okay? So my equilibrium concentration is going to be 0.5 minus X for my acetic acid, and my acetate ion and hydrogen ion is going to be X and X. And now I can set up my Ka expression based on my given value of 1.8 times 10 to the negative fifth. That will give me my hydrogen ion concentration. And then I can find my pH. So my Ka expression is set up this way. The Ka is equal to the hydrogen ion concentration multiplied by the acetate ion concentration divided by the acetic acid concentration, all at equilibrium. Knowing that my Ka value for acetic acid is 1.8 times 10 to the negative fifth, now I can set it up and I can plug in the values that I know. So this is equal to X times X divided by 0.5 minus X. Now, one little thing we can do to help ourselves out. I'll go ahead and tell you the amount of X is going to be extremely small. So small that for this guy right here, we can assume that that's just 0.5, that not a whole lot has been lost, and so we can figure out the concentration of X based on this. So we go from 0.5 minus X to just 0.5. That makes things a whole lot easier for us, okay? And again, it's all because very little of that acetic acid is going to actually dissociate. But we do want to find out exactly how much. So here we go. Okay, so I have 1.8 times 10 to the negative fifth is equal to X times X, which is X squared, by the way. X times X is not 2X. It's X squared, okay? Okay. So I have X squared divided by 0.5. Now I just do the math. I multiply both sides by 0.5 and I get 9 times 10 to the negative 6 equals X squared. I take the square root of that and I get 3 times 10 to the negative third equals X, which also equals the hydrogen ion concentration. Get it? Okay, now I can take this and find my pH. So I simply plug in my hydrogen ion concentration. pH is equal to negative log of hydrogen ion concentration. So that equals negative log of 3 times 10 to the negative third, and I get a pH of 2.52. Okay, so a little more involved with the weak acids than they are the strong acids, but it's important to know how to do it for later on. Okay, here's your problem for the day. I'm going to lead you through it just a little bit, all right? You have 0.04 molar HClO2. That's chlorous acid. The pH is 1.80. Now we're going to work a little backwards this time. We're going to actually find the Ka based on these conditions. Here is the reaction that takes place, the dissociation reaction. HClO2 yields hydrogen ion and the chlorite ion. Now the Ka expression is going to be this right here. A few hints for you. One, I've given you the pH. So you can find the hydrogen ion concentration by taking 10 to the negative pH power. All right? 2, the hydrogen ion concentration is equal to the chlorite ion concentration. So far so good. And 3, to find HClO2, all you have to do is subtract the hydrogen ion concentration from 0.04. And then you'll have everything you need to solve for Ka. Okay? All right, let's give it a try. That's all the time we have for today. We talked today about how hydrogen ion concentration and OH concentration, when you multiply them together in a solution, always comes out to be 1 times 10 to the negative 14th at 25 degrees Celsius. Then we talked about the pH scale and how you can find pH by taking the negative log of the hydrogen ion concentration. We also said that the pOH can be the negative log of the OH concentration. And since we had that inverse relationship between hydrogen ions and OH ions all the time, we said that pH and pOH always add up to be 14. Just like when you multiply these two together, you always get 1 times 10 to the negative 14. We then said that in a strong monoprotic acid situation, you can find the hydrogen ion concentration really easy. It's the same as the molarity. The same goes for a strong base. but things get a little different when we talk about weak acids and weak bases. So to end our time, we did an ice table together. If you want to go back and take a look at that, you can. All right? Hey guys, I hope you have a great day. I look forward to seeing you all really soon. Until the next time, God bless.